So now I want to derive the Dirac points. Let's focus on Dirac points, just like we did in the graphene. And for that, like Hamiltonian is like this: H is 0, f of k star 0, and let's take A1 is equal to A2 is equal to A. I think we don't need that anymore. And now what I want to do is like, so need to expand f of k around these Dirac points, right, which is pi over 2. Around pi over 2a. So let's do that. I think we can save some time doing that in Mathematica. So f of k, actually, do I need to do that? Let me define this just in case I need this function. I think I don't need to define it, but so let me call this T1, and actually I want to define T1 to be undefined, and let's also erase T2 to be undefined. So this is T1 exp ik times a, but a is equal to 1, plus T2 times what was it? T2 times e to the minus ik, e to the x minus ik. Okay, so this is f. And what I want to do is I want to like do the Taylor expansion like what we did in graphene. I think you can also do it with hand, but it's a little bit faster like this. So this is f of k, and I want to, so this series is what the Taylor series is, and I want to expand this k around pi over 2 up to first term, because Dirac is going to be linear. We only need the first term. So then, okay, let's write this. F of k is equal to I T1 minus T2 minus T1 plus T2 times k minus pi over 2a. I think that's correct. I and plus and minus. Okay, that's it. So I want to define, so this thing, I want to define this to be equivalent to my. We'll see y in a little bit. So this piece, I want to define this to be V Fermi. Let's just, I can define things whatever I want. Let's call this P. The momentum defined in reference to k. Then h is going to be 0 I think minus, so this is going to be V Fermi P minus I and y, and this one is going to be V Fermi P plus I and y 0. I think because I wanted to put it this, I'm more familiar with this form. I think now I need to do it like this, minus my, and I want to define this minus V Fermi if you want. Now everything I think works out. And this thing, right? So this is minus is here, this is mi, and complex conjugate is here, V Fermi minus here. Okay, good. And here I want to use Pauli matrices, because whenever you work with 2 by 2 matrices, Pauli matrix is a good basis of matrices, and sigma x is 0, 1, 1, 0, sigma y is 0 minus I 0, and sigma z is equal to 1 0 0 minus 1. And by using this, we see that this is going to be V Fermi P sigma x plus my sigma y. Okay, so right, and so we can also add, let's also consider we can add so-called sublattice potential or sublattice energy difference, which is going to be something like this. For example, H, let me call it H sublattice, is going to be sum over all sides. This is going to be, let me call this mz, which will be clear why I call it mz in a little bit. This is going to be mz ai dagger ai minus mz bi dagger bi. And if you take the Fourier transform, diagonal things are going to be diagonal. It's going to be k mz ak dagger ak minus mz bk dagger bk. And this Hamiltonian is going to modify. Okay, let's take the entire thing. So there'll be mz here, there'll be minus mz here. If there is like a minus, just put minus here plus here. We are just setting this up ourselves anyways. Nobody is giving this. So this is going to be mz sigma z.
How does mz come to
because in the when we were putting the matrix form, so we are writing it like this. Now because of sublattice potential, we have terms like ak dagger ak, but ak dagger ak can only come from diagonals, and bk dagger bk can only come from diagonals. And we set it up so that this one was plus, this one was minus, and then we had this form. Good. I mean, if you have never worked with these things, it looks a little bit unfamiliar at first, but they are really simple. Like you just, it is almost like a vector algebra. So don't be scared. It's just a little bit of experience is all you need. And so we generally write this like some h of k dotted onto sigma, and h of k is in this case V Fermi P, my, mz, and sigma vector in this case is going to be sigma x, sigma y, sigma z. And whenever you have a form like this, spectrum is automatically E of k is equal to plus or minus absolute value of h of k, and which in our case is going to be plus or minus v squared p squared plus, let me call m without any index. M without any index is short for m squared is equal to my squared plus mz squared. You can see there I have two kinds of masses. One mass comes from this hopping difference, and I call this my. There's another kind of mass which comes from sublattice energy difference, and they both gap out. But later we'll see they are not exactly the same thing. They are actually going to be very important when we...
We just call them mass,
yes? Yes, we just defined it, right?
No relation with the mass.
Like this is like an emergent mass, right? The mass as you know it, where does it come from? Who knows? Nobody knows it. But when you put things in a band, and this m looks exactly like the mass you know, right? Like it's almost exactly like Newtonian mass, but it is not electron mass, right? Because this emerged from band itself. If you want, you can actually, we didn't do this because I think Hande Hoca did this, but if you have like a band, you can expand the energy around the minimum, and you can find this m star, and when you have like a whole band, there's a similar thing and they are gapped, you can think about them effectively like mass, but there's no difference. So we have, okay, we derived 1D Dirac equation. And graphene, we had 2D Dirac equation, right? In the relativistic quantum field theory, we have 3D. Generally, people consider 3D, but they can also consider 1D and 2D. Now, I want to consider so-called zero mode. Like this is also some new introduction. It's like some jargon, but nothing to be worried. So let's consider domain walls and zero mode. This is quite generic, but you can also, if I have time, I can also show it in the tight binding model. So if you remember, we had like A configuration and B configuration. Suppose I start with like A configuration, like let me use like blue. If you want, let me use like up for A configuration. So this is like up, 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 right? So this is A configuration. And at some point in the middle, I can just like mess up, right? I can like do an error, and from here on, I can do like down, down, down. So this is B configuration. Config. And so here, the moment you made this error is called domain wall. And the reason I do up and down, this actually behaves exactly like the domain wall in magnets. In the magnets, you have like up spin regions and down spin regions, and the boundary between them is called the domain wall. But here, what we have is like a what we have is, so the difference between these two things is what? So we defined mass to be T1 minus T2. When you are in A configuration, this has one sign, right? Say T1 is bigger than T2. When you are in the B configuration, T2 is bigger than 2, right? The mass changes the sign at the domain wall. That's the only observation we need to make. And here, mass change at sign of mass change at domain wall. And then the question is, what happens if this thing is observed? What happens is we can answer this question by calculating the low energy physics, right? We want to simplify the physics, and we don't have to go back to, okay, we can also do this in tight binding model, but there is a nicer way to do this. We can do it in the effective emergent Dirac Hamiltonian. And in the Dirac Hamiltonian, I'm going to write it like this. Let me forget about the sublattice mass. This is V Fermi P, V Fermi P. And now this, there was like, if you run minus IM, I want to make this, so this is X direction. I want to make this X dependent mass. So mass changes as a function of location. If you want in the magnets, it's going to precess, right? As you go from one to the other, the upspin is going to slowly rotate and align with the other domain. But here we are going to do it the same thing with the mass. This is X0. And because now there's like an X dependence, we are going to promote P to derivative dx. And here, let's take V Fermi is equal to H bar is equal to 1, right? So this is 1, so this is 1. Actually, this is going to be minus I d dx. This is minus I d dx. Good?
How can we say V is Fermi velocity, isn't it?
Yes.
It's just a constant.
Because the slope here is constant, right? The Fermi velocity here, right? We obtain this without any trick. And this is, you can look at the slope. It is, even for small mass, there's like a constant slope, right? And that's the constant Fermi velocity. But of course, at higher energies, that's not the case. We are doing the approximation.
Didn't we have the Fermi as T1 plus T2?
Yes, T1 plus T2, but I take it to be 1, and the other one, like, Yeah, I take this one to be 1 and this one to be m, and I change this as a function of position. And now I can forget about the tight binding model and solve this Dirac equation, because this is first order differentials, right? Easier than anything else. So let's substitute this h d psi1 psi2 is equal to e psi1 psi2. We need to solve the Schrödinger equation. But the interesting thing is that doesn't happen all the time is, let's put epsilon is equal to 0 and see if there's a non-trivial solution. Typically, if epsilon is equal to 0, psi is 0, right? If we can put epsilon is equal to 0 and find a non-zero psi solutions, that's an interesting solution. And that's what we want to do. And if you substitute it to here, right, this is simple. What you are going to do is like minus I d dx psi2 minus I m of x psi2 is equal to 0 because of 0 energy. And the other is exactly the same. But this one is 1, this one is 1, this one is plus, right? Nothing, no difference.
Is 0 energy possible?
Exactly, that's what we are trying to see. If you can find a psi that is not 0, then it means it's possible. And then you have to think what it means, right? That's what we are doing. So let me solve it and show what this thing looks like. So this one is psi2. Let's put it equal here, right? This, and erase this, and erase i's, and this is minus here, and I think it's going to be some coefficient c2 e to the minus from 0 to x m of x prime dx prime. And similarly, this one is psi1 is equal to c1 e to the plus from 0, because this is plus sign, m of x prime dx prime. And for this problem, I want to consider the following domain wall. Let's consider so-called soliton domain wall. And what this means is, I have this x is equal to 0 point. This is x. This is x. This is m. So I want to take this side to be positive, like this, and continuously crank it down, and this side to be negative. Right? This is some plus m0. This is some minus m0, and you transition from one to another. So this one is called soliton. This is also terminology. We don't care about the jargon here. We just repeat what people say. The other one, if this side is plus, this side is minus, people call it anti-soliton. Okay? If you want, let me color blue. So this one, it's just terminology, is and anti-soliton. But for the moment, we are only going to solve it for soliton. And let's look at these solutions. Simple things, but sometimes simple things require some care. So as x, let me also check before if I messed up. Psi1 is c1 plus psi2 is c2. Okay, this is correct. Now I need to consider both x is equal to plus infinity and x is equal to minus infinity. So this psi2 solution, as x goes to infinity, m goes to m0, and I have something like some c2 e to the minus m0x, which is decaying solution, right? It doesn't blow up, so this is a good solution. So then c2 is allowed to be non-zero, whereas this one is going to be c1 times e to the m0x, and it blows up. Then we have to take c1 equal to 0, otherwise it's not a valid solution.
How could we integrate?
I didn't integrate. I said if it is really large, it is constant anyways. The first one. So I said if this is very large, I took out the integral, like this is some approximately some the people call it asymptotically, it is m0 times x, right? Because I know m0 is going to be constant for very large x. I take it out, and what remains is from 0 to x, the x prime, and it's going to be mx. There could be some overall constant, and I absorb the overall constant in C2. So C1 is 0. Now the other side I need to consider, right? If you go to minus infinity, so this is minus. So this one is also minus. Minus is plus, and I have an overall minus, so things do not blow up. So this is still good. And this one is 0 anyways, right? Then we have this this kind of solution here, like which is exponentially decaying. So it decays exponentially like this. And it is form is only psi2 form, right? It is like 0, 1 form, right? Because psi1 slot here is, this one is 0, this one is 1, and there's some exponentials I took out. So if you do exactly the same thing for anti-soliton, what you are going to find is there will be a bound state of 1, 0 type. Right? And soliton will have this kind of bound state, and this is going to have this kind of bound state. These are what we call zero modes. So this is 0. Let me write it in 0 mode. And they have 0 energies. Let me, sometimes people like using these things. Let me mention something called Atiyah-Singer index theorem. This is normally, this could be very complicated, but you can see in this problem it will turn out to be very simple. I want to define some Q. This Q is a different, if you want, like something like a topological charge, and I want to define it like this. This is sine of m infinity minus sine of m minus infinity. In our case, this is plus, and this is minus. Minus is 2. 2 divided by 2 is going to be 1 in our case. And I want to define like number of 2 solutions. So this is n2, and number of 1, 0 solutions. This is n1. And the Atiyah-Singer index theorem says that n2 minus n1 is equal to charge. In our case, n2 is 1, n1 is 0, and q is 1, and the index theorem is satisfied. Like as an exercise, you can check this theorem for the anti-soliton if you want. Now, these are the results. Now we have to think about this a little bit more, and we have to consider symmetry to explain this zero bound state. So the Dirac Hamiltonian HD is going to be equal to, let's forget about V for me. It's like something like the interesting form is here. It is m of x sigma y, and we have not sigma z in the solution we just performed. Let's look at, if there's like a third Pauli matrix, let's look at H Dirac sigma z. It is going to be sigma x sigma z p plus sigma y sigma z m. So what is the so this is anti-commutation relation. What is the anti-commutation between two different Pauli matrices? So you can write the matrices yourself. You can look at their, what's that?
It's both side examples.
Commutation is something like that, but anti-commutation is even simpler. check this, okay? This is the 2 by 2 matrices. If you want, you can write it in Mathematica. This is 0, and this is 0, right? They anti-commute. Then we have 0 anti-commutation. However, in our symmetry arguments, we had H, A, 0. If you can find an operator A that commutes with Hamiltonian, we said H and A can be diagonalized simultaneously. But this is a commutation, right? Now we have anti-commutation. We have to think about this derivation one more time. Let's do that real quick. Suppose you give me a vector H psi, and there's like a corresponding energy E psi, and you also give me there's some operator, let me call it C, that anti-commutes with Hamiltonian. And the reason I use C is typically this is called chiral symmetry, or sometimes it is chiral or particle hole symmetry, which we are going to understand why particle hole. So you give me a Hamiltonian and you give me a symmetry, then what I can do is I can operate with C on both sides. Exactly like I drive in the commutation, I can hit with C here, I can hit with C here, but E is just a number, they just commute, so I have C here, right? Let me use curly E not to mix up. But this piece, they anti-commute. What does it mean? CH plus HC is equal to 0, then CH is equal to minus HC. That's the meaning of anti-commutation. So this is minus H. Actually, let me write it here. Minus HC psi is equal to E C psi. But I can put this minus to here. So, and different from the commutation, what I see is if psi is eigenstate with energy epsilon, or let me write epsilon, C psi is also eigenstate with minus epsilon, right? So this says if you have this C symmetry, chiral operator, for every positive energy, there has to be a negative energy, right? That's why it has to be particle. If you have some spectrum in the positive side, you have to have exactly the same thing in the negative side. That's why we call it particle hole. And now we have to show that this, and okay, let's define psi prime. We have to show that these two states are distinct. This is also very easy to do. Let's consider psi prime H psi, which is equal to epsilon psi prime psi, but I can operate on this side, and this is going to be minus epsilon psi prime, and I can combine everything in the same side. It's going to be 2 epsilon psi prime psi is equal to 0, and if epsilon is non-zero, psi prime and psi are distinct states. They are different states. However, if epsilon is 0, so there can be no pair of epsilon 0, right? Epsilon 0, particle, it cannot have, we don't have 0 with two different signs. There's only one 0. Then there have to be only one state. Then only one unpaired state is mandatory. So you have to have this, and that's the reason for the 0 mode we found. So because of this symmetry, which Hamiltonian, the Dirac Hamiltonian 1D commutes with sigma z, and this automatically mandates epsilon is equal to 0 mode, and when we solve this, we found it to be this bound state. Actually, we can do this calculation in the tight binding model, and what we are going to see is like you have like it's easy. The easiest way to see this is like look at the extreme dimerization limit, extreme dimer limit. Let's put T2 is equal to 0, and we are going to put a domain wall. Like, what does it mean? I go like this, and I go like that, and I go like that, and then at some point I put this, but I decide to put a domain wall, so this guy is going to be by itself, and I'll continue with up down, up down, up down, right? If you want, this is T1, T2, and I put the domain wall, so there's like a single side in the middle. That's the zero mode. Any questions?
John, is there any physical meaning of zero energy?
I mean, zero is like, of course, I think you shouldn't, like, especially when we are doing like energy bands, like, we can shift energy up and down, right? We don't care too much, like, exactly, especially your question too, right? There's like some reference point. We call it, where did I have the spectrum, like here. There is like some reference point, but this reference point can be shifted up and down. Of course, in the Dirac equation, in the relativistic case, you cannot do that. There is like it's a more difficult problem, right? That's why people consider like this the Dirac C. But in the band case, actually, this becomes much nicer. You have like half filling case, all like you have like a reference point which you called zero, and everything below this point is occupied, everything above is empty, and you have actually ideal realization of the Dirac point. So in that sense, that zero is not a big zero. If you want, this is sometimes you can call it E middle of E conduction, something like E conduction, right? Because this, right, solid, I can take the entire solid and lift it a little bit, it's going to have a little bit higher energy. But the problem is, with respect to this reference point, there is like a symmetry. And that's the kind of symmetry we are talking about. Good. So we are almost there. Hopefully you'll see where this initial experiment I told you comes from with this knowledge. Now there's like a problem. The problem, like you can think about 1D tight binding without dimerization or any kind of tight binding model. Like what we know is number of states is equal to number of carbon, number of C atoms, right? We know that however many sites you have that many states. But now it seems like we have like a zero mode, right? Like we have some, let me write it like energy diagram, right? Some energy is something like that. So I have some zero mode here, and I have some continuum here. Now, how did we create the zero mode? So the way we created zero mode is by creating like a domain wall, right? And suppose we have like, let me first pose the question and then I'll explain you the answer. So I have like, so one state, and where does this one state come from, right? Like as you change the bonds, as you put domain wall, you just change T1 and T2. You don't change the number of carbon atoms. You have one more state in the middle, right? Because when you put the domain wall, it is like one more state with zero, but same number of number of C atoms. So where did it come from? It has to come from somewhere. Like you may, like what is your suggestion, right? There's like one more state coming from, but the same number of carbon atoms. Initially, maybe I had something like that without zero mode. So this one. And then the question is, there's no one state, so this second state, where does it come from? Somebody should give this state to us, right?
Hydrogen.
Huh?
Hydrogen.
Hydrogen?
Maybe hybridization or something?
I mean, like somewhere already here should go to here, right? It's going for either from up or down, right? There's no other possibility. Is that clear? Like there's like some state here should somehow evolve, like disappear, and it should give rise to this zero mode. Is that clear? But there is a problem with this. Like if it comes from here and not here, then you break particle Hall symmetry. If it comes from here and not here, you still break particle Hall symmetry. But it looks like to preserve particle Hall symmetry, you have to have 1/2 state from here and 1/2 state from here, and they should combine here as one state. But like, what is 1/2 state? That's ridiculous, right? It's like some stupid thing to say. Like, state is state or not. There's no 1/2 state. Yeah. This is what I start with, right? I have like these single and double bonds. Initially, I have like a perfect polymer without any domain wall. And then I continue, at some point I flip one bond and I just put a domain wall. I don't change the carbon atoms. And I say that this is going to give us a one state.
Does one electron oscillate between around domain wall between two dimers?
Like, it is not about electron, right? It is like there are carbons. It's like about geometry. Now, when we count the number of states, we don't say how many electrons we have. We first count the states and then occupy these states. Now, in this case, there's like one state coming from somewhere and we don't know anywhere, but if we insist that there's like a particle Hall symmetry, it seems like each conduction and valence band are going to contribute 1/2 state. And saying as 1/2 state is a ridiculous thing, so we have to understand that. So for this, okay, let's go back. Okay, the goal is we are going to understand, actually there is a meaning to 1/2 state. It makes sense to say conduction band gives 1/2 state. We will understand that, and then we are going to see how it explains the experiment. So let's go back to boundary conditions. Basically, let's call periodic boundary conditions, right? That's how we count number of states. And for simplicity, let's call even sites and periodic boundary conditions. And what is periodic boundary condition? Like I have a ring, right? And so there is like some site 1, some site 2, site 3, unit cell 1, ... and you come back, and is here, and you connect all of them. And let me put the domain wall around this ring, right? So let's show the domain wall with red, and if the mass is positive, I'll put the circle outside, this red circle outside. If the mass is negative, I'll put the color inside. And I want to put one domain wall, only one. So I start with positive mass. I choose somewhere, let's put domain wall here. I can put anywhere, right? Now I'm inside the ring, so mass sign changed, so this is a domain wall. And but the entire system I want to put one domain wall. I just go like this, and I come back. But what do? Like I persisted one domain wall, but if I have to have periodic boundary condition, I cannot come back to myself, right? What am I going to do here? So the message is, with even size and periodic boundary conditions, it is impossible to create a single domain wall. right? That's like the logic. Then to connect, you can create at least 2 domain walls. So the message is single domain wall is not possible with even sides, number of sides. You have to have 2 domain walls. So let's see how this plays out in the tight binding model. So I have this blue side and red side. I have this, let me use this one, and let me use this one, and I repeat. So I repeat this. So this is 1 unit cell, 2 dot dot dot, right? So this is 1, 2, 3, 4, 5, 6, 7, 8 even sides. And suppose I want to put like a domain wall somewhere. Like what I want to do is, let me erase this. So what I need to do is I need to put, okay, I need to also draw my unit cells. Let me try to reproduce what I did here. So this is my unit cell. So let me repeat one time, and I want to put a domain wall here. So here's my domain wall, and I want to, in the second one, what I need to do is, in the second one is, I have like blue, red, and so this is blue, and this is red. But for the next point, if I had the solid line, there would be no domain wall, right? For me to have like a domain wall, this needs to be dashed line. So this is also dashed line, and this is solid line. Now the unit cell is like this, and now I can repeat this, dot dot dot. But now I have to connect. So I have even sides, 1, 2, 3, 4, 5, 6, 7, 8. At the end, I need to connect this side back to here. But connecting back to here means what? I have like a solid bond, one more solid bond, right? I have solid dash, dash. I have one domain wall, and then dash, solid, solid, one more domain wall. So there's 2 domain walls. So we draw it with the ring, but you can actually see this thing in the tight binding model too. So then what happens is, here let me summarize what what this means. Okay, sorry, it is a little bit confusing, I know, but it takes a little bit. I mean, this thing was discovered in 80s, right? People could write, this is like single particle tight binding. It could be written 100 years ago, but they didn't, for a reason. So soliton takes 1/2 from conduction band, and anti-soliton takes 1/2 from, again, conduction band. At the end, 1/2 plus 1/2 is equal to 1. Conduction band is going to give only one state, right? So they don't separate. Similarly, so by the way, if this is soliton, right? This is like 2 dashed lines. This is soliton. This is 2 solid lines. This is anti-soliton. And okay, this is valence band. So this is, a soliton takes 1/2 from valence band. Anti-soliton takes 1/2 from valence band. In total, there's 1/2. So what happened is, both conduction band and valence band, they gave you one state, and it is in a total 2 states. but each state you split, put one half in the soliton, the other half in the anti-soliton, and then take the other state, split, put one half in the soliton and the other. Okay, that's what you do.
I can't catch the physical meaning of one half state.
Like this is the physical meaning, right? Like so we have, if you like thinking about like a tight binding model, physically that's what's happening. And if you want to think about this, we have like this. And at the end, conduction band and valence band, they give one state.
Can we think half state separately, totally separate from this stuff?
That we showed we cannot, right? We showed that you cannot think about a half state by itself. In an even side periodic boundary condition, it has to be another half state somewhere else. A half state always requires another half state somewhere else. That's why they are always, they come in soliton and anti-soliton pairs.
So instead of saying we can put a single domain wall, should we say odd number of domain walls?
Yes, like you cannot put odd number of domain walls. You can only, like if you have even sides and periodic boundary conditions, domain walls always come in two pairs, right? You can take somewhere here, you can go up, there's one domain wall, but you have to come down, there's another domain wall, right? You can pick another point, you just go up, you come down, there's always two crossings, and two crossings always require two domain walls. Okay, we can talk about this a little bit more. Let me give you the explanation of experiment and then finish it there. I think there's so much to talk about this. And you can see it's a simple model, but there's a lot of things. Now, a zero mode is a state, and it can be occupied, it can be unoccupied, it can be occupied by it can be zero, it can be up, it can accommodate up electron, down electron, it can accommodate up down electron. These are all possibilities. And when I dope this system, right, in the earlier hour, in the experiment I showed you, we introduce electrons, and these electrons prefer to go and sit on these zero modes. And these zero modes, if it's not doped, they have zero electrons. If it's doped, it can have up, down, or up, down electrons. Now let's do the counting. There are four possibilities. Possibility 1, zero mode, empty. But empty zero mode means what? A field valence band lost 1/2 state, right? And a 1/2 state is equal up and down. And so this is what we need to take into account. An empty zero mode because like this state is lost from the valence, right? We are saying that there's like a conduction band and valence band. Valence band is fully occupied, conduction band is fully empty. If something is missing here, it is a hole, and a missing electron is like going to have like a positive charge. So it's going to be empty zero mode will correspond to a positive charge. But because this came with both up and down spins, no spin. This is what we are considering, like zero mode, which is unoccupied, has plus charge but no spin. So the second possibility is zero mode with one up electron. I think actually let's consider this one up down. This is a little bit easier. So again, the same thing. Field valence band. This guy is going to have plus E charge and no spin, and zero mode is going to have minus 2e because it has like 2 electrons, and because it's up and down is equal to no spin. So here we have plus e, minus 2e plus e is going to be minus e, right? So then 0 mode empty is a positive charge, 0 mode is fully occupied is negative charge. And let's consider last one, 0 mode with only up electron. Again, filled valence band which contributed to this mode is like plus E and no spin, but 0 mode is going to be minus E, but now there is only one spin, and in this case if you sum this up you have Q is equal to 0 but spin is up. Okay, it's a little bit too many things to consider, but it's really like just adding up numbers. So what we have is like we have, if you want, we split the electron and we separated charge and spin, and that's the reason for this experiment in the beginning, right? So you can have charge without a spin, or you can have spin without a charge. Good. Okay, we are going to be talking more about this, don't be worried, but I suggest you make the derivation. At least this tight binding calculation is doable, and once you see the derivation it's not going to take more than 30 minutes. Please do it. But other details, how this counting comes about, we are going to repeat a couple of times.